start recording again. Thank you. So back to 2.9. And as I said, what I want to do is kind of one example all the way through. So much of it is similar language to what you had in Calc 1, which is critical points are where the derivative is 0, that now it's the gradient, or the derivative isn't defined. As with Calc 1, the second part really isn't going to come up much. But in theory, it could. And we're going to need something more general than just second derivative to decide if something is a max or a min. You don't need to know the name, but what's called the Hessian matrix of a function is defined to be just the matrix with all these second order partial derivatives, where the first row is all the partial derivatives where we start with x. Hessian. Hessian. So if it's three variables, then you would have a 3 by 3, where you'd have fxx, fxy, fxz, ... We don't do anything except for 2 by 2s because it starts getting much more complicated. So we're only going to look at local extrema for 2 variables. Definition. And this is pretty much the only type that we're going to run into. The point is called a non-degenerate critical point if the gradient is 0, the 0 vector, and the determinant of the Hessian is not 0. And in some ways, you can see how this would be kind of something we wouldn't care about. For example, if we have something that's linear, then all the second derivatives would be 0, and so therefore this determinant would be 0. And the reason that it's not something we care about is, well, there aren't any minimums and maximums for something that's linear. So usually, if this determinant is 0, then it just means it's a really simple function where there might not be minimums or maximums. There are cases where it's more complicated, but we don't run into those. So for us, pretty much everything we see will have this be non-zero. So here is the expanded second derivative test. And unlike the one variable one, the other versions aren't as nice. It's hard to graph the three-dimensional thing. The first derivatives are kind of a pain because you have to look all around the circle. So second derivative test ends up being the nicest. And let me remind you, put this back up here. And let me talk about it with this one. So in some ways, you can see how this would be a generalization. So if we ignore the fxy, then if d is bigger than 0, and the only way that works is if fxx and fyy are both positive or both negative. So one is saying if that's true and positive, so I say fxx, but they have to be the same for d to be positive, then that means that they're concave up, which we're thinking of as the minimum. And kind of in a similar way, if d is more than 0 and both of them are less than 0, and it's concave down, and we're thinking a local max. And if it's less than 0, the most basic way that happens if the two second partial derivatives are opposite. So, for example, fxx is positive and fyy is negative, which is saying, well, looking at it from one way, I'm getting a maximum. Looking at it a different way, I'm getting a minimum. And so therefore, I'm getting a saddle. This is needed because if this mixed one is big enough, even if both fxx and fyy are the same, it could be that something weird is happening in between them. So that in between, it's changing from a min to a max. So kind of a generalization of it. So let's see if I can get through a problem. Here's an example. Let's start off with a fairly straightforward one. So as with one variable, first step is to get critical points. So take the two partial derivatives. Set them equal to 0. In this case, as I said, I've made it nice, but in general, the partial derivatives can involve both variables, of course. And so it becomes a bit more complicated. But so you can see in this one, if I solve for it, I get 3x cubed is equal to 1, 3x squared. So therefore, x is equal to plus or minus 1. In this one, we get 3y squared is equal to 24. So therefore, y is equal to plus or minus 2. And since we need both equations to be true, I need both things to be true. So we get, well, one thing that would work is if x is negative 1 and y is negative 2, x is negative 1 and y is positive 2, and then 1 and negative 2 and 1 and 2. Oh, yes. I lost the routine. 18, thank you. So these are critical points. And now to decide what each of them is, now we get the Hessian, all the second derivatives. So second derivative with respect to x is 6x. Second derivative with respect to y is 6y. And the mixed is 0. So as I said, kind of a simple one. And therefore the determinant is going to be the 36xy. So if I put in the negative 1, negative 2 square root of 2, I get positive value. I'm not going to give a number because it's not going to be nice. It's going to be 72 squared, I might as well, 72 squared root of 2. That is more than 0, which, as I said, is showing that both second order ones in this case are negative, which means they're the same. And we know that fxx is less than 0. So the first part is telling us that they're the same, which means it's probably going to be a minimum maximum. This tells us it is a local maximum. And then I just go through all the other ones. So if I do the negative 1 and positive 2 square root of 2, then now I'm going to get negative this. And that's because one of the seconds is positive and one is negative. And that's telling me it's a saddle point. So it's telling me in one direction it's a minimum, in one direction it's a maximum. So I'm at a saddle point. And then the other two are just similar. So I do 1, -2, I get the same thing. Well, saddle point. And if I do 1, 2 square root of 2, 72 square root of 2. So these are all pretty much the same numbers. So here is the run through how we do it in general, which is very similar in some ways to the first one. Take the derivative, set it equals 0 and such, just that now we're getting vectors. Take the second derivatives to see if it's a minimum or max. Except now we have the third option, which is it could be a saddle point. So one example, and obviously we'll have to do more, so that's what we'll do tomorrow at the beginning. But let me ask, go back to Calc 1. Once we did this, which is we're deciding if we have local minimums or local maximums, what is the next step? What we want to get is global minimums and global maximums. So we want to do optimization. And similar to Calc 1, I wouldn't really want to do it for this general one because there might not be a global minimum or maximum. And it gets really kind of annoying to check it. But what we would do is saying if x and y are both between 0 and 1, then what is the global minimum and global maximum? So given a restraint, what's the global minimum maximum? And we know from Calc 1 that the way you do it is you find all the critical values, and then you look at the endpoints. And what's going to be more complicated here is now instead of just endpoints to plug in, we're going to have a whole two-dimensional object type thing that we might have. So tomorrow we'll do probably one more example of this. I'll probably do a quick one where we do the global maximum. Probably one of each. That will take up the half hour. And then the rest of the time for the quiz. So any questions on this? Right, so let me stop here. As usual, if you have questions, stick around. Otherwise, I'll see you tomorrow for the quiz. I'll stop recording.